All right, so here we are. Now let's talk about valence electrons. So aluminum is in group 3. So you write the symbol for aluminum, and then you draw 3 dots. Just 3, because we just want to draw the dots for aluminum's valence electrons, not all of them. It's got 13 total electrons, but we only care about those 3. Helium. Helium's tricky because it's in group 8, but it doesn't have 8 valence electrons. It gets to hang out with the big guys over there. It gets to hang out with the noble gases because its first energy level can hold 2, and that's exactly what helium has. And that first energy level, the only energy level, is filled, so helium's got 2, and it's nice and happy, so it gets to hang out, not in group 2, with the rest of them that want to give away 2. It gets to hang out with the noble gases in group 8, even though it's only got 2. All right, potassium's in group 1. Potassium loves to get rid of that 1 valence electron. Even though it's got 19 total electrons, we don't care about 18 of those. We only care about the 1. Silicon is in group 4, so it's got 4 valence electrons. All right, so now the nucleus exerts a force on those valence electrons. And we have to decide, does that attraction between the valence electrons, which are negative, and the nucleus, which is positive, does that become stronger or weaker as you move across a period? Remember, period is a row, going from left to right. So if we compare lithium with any of these other elements in the same row, same period, then what we see is an increase in the atomic number, but increase in the number of protons inside the nucleus. Now, that makes the nucleus a tiny, tiny bit bigger, but we don't really care about that. What we care about is the overall size of the whole atom, and we'll talk about that when we get to atomic size. But what's really important here is that the nucleus gets stronger. The more you go to the right, the stronger that nucleus is, and the more it pulls on those valence electrons. And that's going to be a major factor in a lot of the different trends that we see. So if we had to compare lithium versus neon, and they're in the same row, same period, and we had to decide which nucleus exerts a stronger force, we would say neon does, because it's over on the right, it's got 10 protons versus lithium's 3. So the more you go to the right, stronger the nucleus. Picture that all the time, and that's going to come into play when we talk about trends. Shielding effect. Now let's take a look at what the shielding effect is. Now, if you are, or if I am a teacher, and you guys are my students, and you are sitting really, really close to me. Here's the teacher in the front of the room, and here's you. You are really close. I get to see pretty much what you're doing. There's not many kids in the way. But if you're a kid and you're sitting way in the back of the room, and I'm way up here in the nucleus spot in the front, then I might have a hard time seeing what you're doing. I might have a hard time keeping tabs on you because there's so many kids in the way. That's what we call shielding effect. It's not kids in the way in the atom, it's electrons in the way. So the more energy levels we have, and you get more and more as you go down the group, the more energy levels we have, they're all filled with electrons, the more they block or shield the nuclear pull on the valence electrons. And that has ramifications for our trends. For instance, if we look at the first trend, which is atomic size. As you go across a period, what happens to the size? Well, as we go across, you see here the size gets smaller. And that's kind of weird. And you're thinking probably that neon should be bigger because it's got 10 protons and 10 electrons, and lithium's only got 3 protons and 3 electrons. So why on earth is this smaller than that? And the answer comes down to that nucleus. The nucleus on the right is stronger. So if you have 10 protons, yeah, the nucleus gets a tiny bit bigger, but the electron cloud gets pulled in tighter because this is a stronger nucleus than over here. So remember we used the analogy of the marble on the 50-yard line of Giant Stadium when we talked about the size of the nucleus compared to the size of the electron cloud? That nucleus, if that gets a tiny bit bigger, it doesn't make a big change in the overall size of the atom. The electron cloud is what we're concerned with. The volume of the atom, remember, the majority of the space taken up by the atom is that empty cloud. The nucleus is where all the mass is, but it hardly takes up any space. So if that little dot goes from there to there, it's not changing the size of the electron cloud much. In fact, it's just getting stronger, and it's pulling the electrons in closer because there's a stronger force between these negatives and that positive. So that's why it gets smaller. Stronger nucleus gets pulled in tighter. As we go down, we add more energy levels. So this is group 2 of the periodic table. So they have 2 energy levels. This is group 3, 3 energy levels, and so forth. So there's more and more energy levels added, and the size gets larger. Now the next question says, explain 2 ways atoms can become stable. Well, the first way atoms can become stable is by making ionic bonds. We can make ions if we have a metal and a nonmetal. So if we have a metal, the metal always wants to get rid of an electron. So here's the 1 valence electron that sodium wants to get rid of. And little chlorine saying, hey, that's great. I have 7. I need 1 more. So sodium, if you could just give me that electron, that'd make me really happy. And it would make you happy because you go from having your 3rd energy level with 1 electron to your 2nd energy level's got 8 and it's nice and filled. So as soon as you kick out that extra electron, then this 2nd energy level becomes your outermost, and now you're happy when you end in 1s2, 2s2, 2p6. You've got your 8 in the 2nd energy level, and sodium's good. So anyways, sodium loses an electron. When you lose an electron, it's not minus. Minus does not mean subtract in this case. When you lose an electron, you end up with more protons than electrons. So you have a positive 1 charge. And chlorine gaining 1, so it has a negative 1 charge. And what do you get when you have a positive and a negative next to each other? You get an attractive force between them. So that's an ionic bond. So you need a metal, you need a nonmetal. The metal is going to get rid of the electron. Where is it going to go? Over to the nonmetal. And that makes an ionic bond. So that's one way we can become stable. Make ions, and then they're attracted. Ionic bond. The other way we can become stable is by sharing electrons and making covalent bonds. Now, here's the deal. When only nonmetals are present, covalent bonds will form. Normally, the metal gives the electron to a nonmetal. Here's oxygen. Now, oxygen is in group 6, so it's got 6 valence electrons. It's got 8 total. 2, 4, 6, 8. It's got 8 total because remember it's 8 protons and 8 electrons. But 6 of the electrons are the ones we care about, the valence electrons out here in the 2nd energy level. So normally the metal says, here, take my electrons. You can take 1, put it there. You can take another 1, put it there. And you can have all 8 and everybody's happy. You get a -2 charge. I make a +2 charge and we're attracted. We make an ionic bond. However, when the metal is not there, that can't happen. So if we, let me erase this here. If we look around and say, well, where's my electron to get, or my metal to give me those 2 electrons, and we realize there's not 1 there, metal's not present in the container, then we end up with just oxygens looking at other oxygens and saying, well, you have 6 and I have 6 valence. What are we going to do? How are we going to get 8 together? And they decide, let's share. Let's pool some electrons. So this is kind of what they do. They take some, and we're going to talk about this a lot more when we get to Unit 5, Section 2. But they take some of their electrons and they decide, let's send them around you for a while, and then send them around me. And then they'll go back around you and back around me, and so forth. And as long as each nucleus is pulling with the same amount of force on those electrons, then they get shared 50-50. So they spend 50% of their time here, 50% of their time there, and both atoms think they have the octet all the time. Everyone's happy, and that passage of electrons back and forth between the 2 clouds is a covalent bond. So this happens when there's no metals around. The metals can't donate electrons because they're not there. So covalent is when the nonmetals have to cooperate. CO, covalent, cooperate. And they fix themselves somehow and they become stable. All right, Mendeleev. He arranged his periodic table based on mass and the properties. Now, at the time he created his periodic table, they didn't know about protons, so they didn't know about atomic number. So he arranged everything based on mass, which typically does go up. However, we've since rearranged it according to atomic number, which is basically equal to the number of protons, and still the properties and behaviors of the elements. Like, that's how we know when to end a row on the periodic table, when to start the next row. For instance, here's neon in group 8 of the periodic table. This is element number 10. 11 doesn't go here. 11 is sodium. We don't put 11 after it. We put 11 over here again in group 1. Why group 1? Because it acts just like lithium and it acts just like potassium. So we don't want to keep going. We say, hey, this repeats. We've seen this property before. Let's put it with the other guys that share the same properties. So that's how we know, start a new row, put the elements together in the same group that have the same properties. Another cool thing that Mendeleev did is he predicted. He looked at elements above and below where elements were missing, and he used them. He averaged their properties, and he predicted what elements were going to be discovered and what they were going to look like, and their melting point, and their boiling point, and their density, and their appearance, and how many oxygens they bond with, and how many chlorines they bond with, all sorts of crazy stuff, and he was pretty much dead on, and people were amazed at the way he could use his periodic table as a tool to help him predict things, as well as organize stuff. Why do elements in the same group share similar properties? It's all down to the electron configurations. They all have the same ending, and they all have the same number of those valence electrons. So lithium ends in 2s1. Sodium ends in 3s1. Potassium is 4s1. They all end in the same electron configuration, and they all have the same valence electrons. So therefore, they behave the same way. And finally, which group of elements on the periodic table is most unreactive? The good old noble gases. These guys are nice and happy because they have their octet. Helium has its 2, that's all it needs. It's happy that way, but everybody else has 8 in the outermost energy level, so they're stable as they are. They don't need to do anything, whereas every other element on the periodic table is not happy, doesn't have that stable noble gas configuration, so they're looking to do interesting things such as gain, lose, or share electrons. And that's why they bond and noble gases don't.